Welcome back to the wonderful world of physics. This is section 22 on Coulomb's law. Coulomb's law is given on the page there. It's the idea that there is an attraction or a repulsion, a force between two electric charges. And the force is given by, you see the equation in the box, some constant, and we'll call this the Coulomb constant, K, 8.988 times 10 to the 9th newtons meters squared per Coulomb squared, times the absolute value of the first charge times the absolute value of the second charge divided by their distance squared. Now this is a scalar equation right here, and it doesn't take into account the positive or the negative. This just gives the magnitude of the force. This is a very important constant that you'll be using much in this class. However, if you look in the front flap of your book, it's not given. With all the important physical constants, it's not there. Now you can look in the front flap of your book and you'll see a K, but that's Boltzmann's constant, 1.38 times 10 to the negative 23rd joules per Kelvin. And that's not this K. This is another K. And if you're wondering, why isn't this important constant there? Well, because actually it's based on another constant, which is in the book, permittivity constant, which is epsilon naught. But we'll get to that at a later time. The Coulomb equation as a vector is given by this equation down below. Force of 1 on 2. Now we can think of that as the force by charge 1 on charge 2, and it equals K times Q1 times Q2 over R squared. And notice there's no absolute values, so if Q1 or Q2 are positive or negative, we include that positive or negative in there. But then times the unit vector R hat. So you've had I hat, which is the unit vector in the X direction, J hat, the unit vector in the Y direction. This R hat is the unit vector that points directly from Q1 to Q2. So again, the force that Q1 acts on Q2, this equation is going to point it in the direction going from Q1 to Q2. Now, it could be in that direction, it could be in the opposite direction, but that will be settled by whether Q1 and Q2 are negatives or positives. So we have this picture right here. Here are two positive charges, Q1 and Q2. And if we were to plug the charges in, they're both positive, so we plug them into the equation. And since they're both positive, then it'll point in the direction from Q1 to Q2, as you see there. So Q2 is going to be pushed away. But rather than thinking about which way the vector is supposed to go with the positive and negatives, it's actually easier to just use our good sense from the idea that opposites attract and like charges repel. So these two charges, since they're positive, they will repel each other. Based on that fact alone, we know that the force that charge 1 acts on charge 2 is going to be to the right. And the force that charge 2 acts on charge 1 is going to be to the left. And here we have right there, we can also see from Newton's third law that that's true. The force from 1 on 2 goes to the right, the force from 2 on 1 goes to the left. Now, if they are opposite charges, then if you go back up to the equation, it doesn't matter which one is positive and which one is negative, but if they are opposite, meaning one of them is positive, the other's negative, then this entire expression is going to be negative, which means the force of 2 acting on 1, or 1 acting on 2, whichever one you're going to do, is going to be in the negative direction. So if you look at this example here we have a negative and a positive charge. If we want to know the force acting from charge 1 to charge 2, well, the equation says to send it in the unit vector direction from 1 to 2, which is to the right. However, remember, the positive charge times the negative, it's going to go in the opposite of R hat, which means to the left. And here you can see we can use our good sense and just say, well, they attract each other. So of course, 2 is going to be pulled to the right and 1 is going to be pulled. I'm sorry, 2 is going to be pulled to the left and 1 is going to be pulled to the right. Here's an example in the book. Example 21, called Finding the Force, 2 charges. It says a 1 microcoulomb charge is at x equals 1 centimeters, and a negative 1.5 microcoulomb charge is at x equals 3 centimeters. What force does the positive charge exert on the negative one? How would the force change if the distance between the charges tripled? All right, so we have our equation here in vector form. We have the force of the positive on the negative. So we have our K, 8.988 times 10 to the 9th, times the first charge, 1 microcoulomb, that's 1 times 10 to the negative 6 coulombs, times the second one, negative 1.5 times 10 to the negative 6 coulombs, divided by 0.02 meters, their distance, squared. Now, it's times the r hat, which, since this is along the x-axis, we can also say that's also the I hat direction. So we plug these values in, and we get the force of the positive on the negative is negative 34 I hat newtons. The negative and then the I hat come together, so negative 34 I hat newtons, which means that it's being pulled to the left. And we already knew that without running the equation, because we know that a positive and negative charge will attract each other. Now, very often it's convenient to not think about the vector equation, but more simply think of the scalar equation. So here's the non-vector solution to that problem. The force is K times, and then you just use the absolute values of the charges, disregarding any negatives, and we get 34 newtons. And then we think, is the negative going to be attracted to the positive or repelled? Well, they're opposite, so it'll be attracted, so it'll be pulled in the negative x direction. So again, we could say negative 34 I hat newtons. The second question asks, what if you triple the distance? Well, if you triple the distance, you could go ahead and plug the numbers in, but and see what a calculator says. But I hope you can see that if you turn this from 0.02 meters to 0.06 meters, you're dividing by another 3 and then squared. So by tripling the distance, you're decreasing the force by a factor of 9. So that would be negative 3.8 I hat newtons. An interesting thing to do is compare the strength of the electric force with gravity between an electron and a proton. So we can figure an electron, proton, we can think of them inside an atom, but it really doesn't matter whether in the same atom or not. So let's find the ratio of the force, the Coulomb force versus gravitational force. So we'll see, is the electrical force, is it stronger or weaker, at least between a proton and electron, than gravity? And so as we set up this ratio, we have K Q1 Q2 over R squared. We're just using the absolute values over G M1 M2 over R squared. That's the gravitational equation that we found last semester. The distance actually divides out, and we're left with K times the charge, the elementary charge squared, over G, mass of an electron, mass of a proton. We can plug all those values in, and here, just for a rough order of magnitude estimate, it's close enough, but for K, I've just used 9.0 times 10 to the 9th, so that's good to 2 significant figures. And here I've done orders of magnitude. So my 9 times 10 to the 9th, I've just rounded that to 10 to the 10th. My G, or my elementary charge squared, 10 to the negative 19. I've just called that 10 to the negative 38, again, just order of magnitude. And you can see here I've done order of magnitude estimate, so I get about 10 to the 39th. So that is how much stronger between a proton and electron the electric force of attraction is over gravitational, which is why when we talk about electric charges, we don't deal with the gravitational attraction between them because the Coulomb force is by far overwhelming by more than a trillion times. Let's look at a two-dimensional example in the back of the chapter. This is number 42, and we'll see how we can do this when there's two-dimensional vectors going on. So number 42 says in the figure, and you can see I've drawn the figure with the charges and the relevant forces. Q1 is 68 microcoulombs, Q2 is negative 34 microcoulombs, and Q3 is 15 microcoulombs. Find the electric force on Q3. All right, so I've written it this way. The sum of the forces, and it's going to be the superposition principle, meaning we're going to find the force from Q1 and the force from Q2, and together, those vectors added together are going to be the net force on Q3. I'm going to treat this not using the vector equation, but I think it's easier to use the scalar equation and then work with the directions from there. So let's look at the force from 1, and that's going to be K times Q1, Q3, of course the absolute values, over the distance between 1 and 3 squared. So we have 9 times 10 to the 9th times the 68 microcoulombs times the 15 microcoulombs divided by the distance squared is 5. Now we get that from Pythagorean theorem. So we have it's 2 this way and 1 this way. So Pythagorean theorem gives that distance between 1 and 3 of square root of 5, but we're squaring it, so 5. And we get 1.836 newtons. We can find the tangent of that angle, of this angle that my pointer is tracing, and it becomes 26.565 degrees. So that force is going at a 26.565 degree angle, and it is pointing in the direction I've pointed it simply because of that they are like charges. Now, let's look at what charge 2 is doing. Well, it's attracting charge 3 because those are opposite charges. So the force that 2 is acting on 3 is K times Q2, Q3, again, absolute values times the distance between 2 and 3 squared. And you can plug those in, and their distance is 2. So we're going to square it and get 4. And we get 1.1475 newtons. And the angle, obviously, it's straight down in the negative y direction, so is 270 degrees. So now we have our two force vectors, and we're going to just do the addition of those force vectors. So in the x direction, we have the x component of force 1 plus the x component of force 2, which is thinking back to very early in first semester, that's F1 cosine theta 1 plus F2 cosine theta 2. So 1.642 newtons for force of 1 plus 0 for force of 2 in the x direction. So we get 1.642 newtons in the x direction. In the y direction, it's F1 sine theta 1 for the y component of force 1 plus F2 sine theta 2 for the y component of force 2, and we get negative 0.326 newtons. So then we can add those up vectorially, and we see that the sum of the forces, the net force acting on charge 3, is 1.6 I hat minus 0.33 j hat newtons. And that is the end of section 22. Have a great day.